All right, so let's talk about salts and buffers. Turns out these are fairly related topics. That's why we're including it in one video. Fairly important as well. I would say it varies from year to year, but you can expect at least 1 to 2 questions on your final exam to cover these two things, salts and buffers. So let's get started. We're going to start with salts. So what is a salt? It's an ionic compound made up of two things, a cation and an anion. And typically the cation is what we call the conjugate acid. For instance, for ammonia, the conjugate acid of ammonia, NH3, would be ammonium, NH4 plus. The anion represents your conjugate base. So for instance, for hydrochloric acid, HCl, the conjugate base of the acid would be chlorine minus, Cl minus. So because they're composed of conjugate acids and bases, salts can have acidic or basic properties. Not all of them do, but some of them can if the base and acids lead to differences in pH. And while they're made up of cations and anions, which individually have charge, the salt overall will always have a net charge of 0, so it'll be neutral. So probably the most common example of a salt that you've seen is the stuff that we basically sprinkle on our food, right? Sodium chloride, NaCl. So this diagram basically just shows how sodium and chlorine bond. That the sodium donates an electron to the chlorine because the chlorine wants one more electron to reach its full octet. What happens is sodium becomes positively charged, chlorine becomes negatively charged, and they have an electrostatic attraction towards each other because opposite charges attract each other, and that electrostatic attraction is called an ionic bond, right? And so that is what a salt is. So one thing that you'll be responsible for on your exam is to calculate the pH of a salt. It's not very different from calculating the pH of an acid. There's just a few steps that are slightly different, but we'll go over it in this problem. So it says calculate the pH of 0.4 molar NH4Cl given a Kb value of NH3 ammonia of the following. So let's go ahead and give this one a shot. So the first thing I would do is kind of separate my salt into its two constituents, right? One is the NH4 plus, and then one is the Cl minus. Now, one of these things is going to contribute to the pH, and the other is not. In this case, we know that NH4 plus is the conjugate acid of a weak base, which means that the NH4 plus is acidic, whereas the Cl minus is the conjugate base of a strong acid, right? This comes from HCl. And then HCl is a strong acid. So we know that HCl is a strong acid, which means that the Cl minus is not basic. So even though it's a conjugate base, it does not contribute to the pH. So we don't actually even have to look at the Cl minus. All we're focusing on is the NH4 plus. And we know that a concentration of that is 0.4 molar. So what I would start by doing is writing basically what NH4 plus does in a solution. So in a solution of H2O, what it's going to do is NH4 plus is an acid, right? We know it's an acid, and what do acids do? They can either donate or, right, the two choices are either donating or receiving protons, and we all know that acids are proton donors, and so it's going to become NH3 after it donates a proton to the water, causing the water to become H3O plus, hydronium ion, which really for all intents and purposes you can interpret as H plus. We're going to do our ice chart, ice table, as we've seen many times before. My initial concentration of NH4 plus is 0.4. H2O is just a liquid, so we don't have to deal with concentration there, and I start with 0 and 0 of NH3 and H3O plus. Minus X, plus X, plus X, and then I can fill in my equilibrium concentrations as 0.4 minus X, X, and X. So what I know at this point is my Ka is equal to the concentration of NH3 times the concentration of H3O plus all over my concentration of NH4 plus. What I don't know is the value of Ka, right? But I can figure out the value from Kb. And the relationship that you should know is that Ka times Kb is equal to Kw, where Kw is 1 times 10 to the negative 14th. So given this information, you can actually calculate Ka from Kb. So basically in this case, Ka is equal to Kw over Kb, which is equal to 1 times 10 to the negative 14 all over KB, which is 1.8 times 10 to the negative 5. Put that in your calculator, and you get 5.56 times 10 to the negative 10. So that's your value of Ka. Now that you know the value of Ka, you can plug in, right? So you just basically write 5.56 times 10 to the negative 10 is equal to my concentration of NH3 times H3O plus, that's x squared, all over 0.4 minus x. And we've probably seen this many times before. We can assume that x is really small, allows us to ignore this term. I multiply both sides by 0.4, I take the square root of that, and I find that x is equal to 1.49 times 10 to the negative 5. And that's my H3O plus concentration. And then finally, to figure out the pH, I take the minus log of that. So minus log of 1.49 times 10 to the negative 5. Put it in your calculator, and you get 4.82. Now, this should actually make sense intuitively because we're dealing with an acid, something that's acidic, right? It has a conjugate acid here. And we would expect the pH to be lower than 7, which is characteristic of an acid. So that's how you determine the pH of a salt. All right, so it turns out that salts can lead to the formation of buffer solutions. So what is a buffer solution? It's a solution that resists changes in pH when small amounts of H plus or OH minus are added. So it's basically something that is resistant to large pH changes. So an example, a biological example, is like blood, right? You don't want the pH of your blood to change drastically if you add small amounts of H plus or OH minus. Here we see a titration curve, and this little region right here where we see that the pH is not changing despite the addition of NOH, that's called the buffer region. It's basically a region where pH doesn't change. And notice that over the course of the titration curve, there's kind of like two buffer regions. There's before that central point and after. This is characteristic of titrations where we have equivalence points, half equivalence points, etc. We'll talk about this in the next video. Also will be very important. But for now, know that buffer regions resist changes in pH. So there's two ways to make a buffer solution. The first way is to mix a weak acid with its conjugate base, which can come from a salt, or mixing a weak base with its conjugate acid, which also can come from a salt. The key thing is like common ion. So basically what I mean by that is you'd have to mix like HC, I don't know, let's say acetic acid, HC2H3O2. You need to mix that with its conjugate base specifically, so C2H3O2 minus. That would be a buffer. You can't mix it with the conjugate base of some other acid. That's not going to work. Okay, so there's an equation you can use to solve for the pH of buffer solutions, and it's the Henderson-Hasselbalch equation. Very important. So first thing, let's consider the dissociation of a weak acid. So a generic acid would be like HA, and in the presence of a solution, it'll dissociate into H plus and A minus. Now, we can use an equation to solve for the pH of this acid in the presence of a common ion. An acid in the presence of a common ion is a buffer by definition. That's what a buffer is. So a question that always comes up is, how do you know when to use the Henderson-Hasselbalch equation? You use the Henderson-Hasselbalch equation if you're asked about a buffer. So if you see the word buffer in the question, that's a dead giveaway that you're going to use the Henderson-Hasselbalch equation. And what the Henderson-Hasselbalch equation looks like is the following, right? You can calculate pH if you know the pKa, which is the minus log of the Ka, plus log of the conjugate base, A minus, all over the acid, HA. So this should work all the time. Depending on the problem, you'll have different unknowns. Maybe sometimes you're looking for a pH, maybe you're looking for the concentration of the conjugate base. You can always use this equation to solve for whatever it is you're looking for. Now, there is a thing called maximum buffering capacity. This is basically where the buffer is most effective and can most effectively resist changes in pH. Maximum buffering capacity occurs when the concentration of the conjugate base is equal to the concentration of the acid. So occurs when A minus, concentration of A minus, is equal to the concentration of HA, right? And when this happens, these guys cancel out. So log of 1 is going to be 0, and pH is equal to pKa. So when these two things are true, you're at maximum buffering capacity. So let's use that equation to solve this problem. So the problem says calculate the pH of this solution of 0.08 molar acetic acid and 0.04 molar sodium acetate. All right, so let's give it a shot. So so the first thing you should be thinking is you have an acid and a salt. So you have an acid and a salt. And the salt contains the conjugate base. So then what you should be thinking is, well, what happens when you mix an acid with its conjugate base? You get a buffer. Right, so this is a buffer problem. Dead giveaway that you need to use the Henderson-Hasselbalch equation. So then I would write pH equals pKa plus log of A minus all over HA. Now, I think you'll probably get this equation on your formula sheet for your class. This isn't something you absolutely have to memorize, but you should be familiar with it. All right, so we're looking for pH. Our Ka is given to us. It's going to be the minus log of 1.8 times 10 to the negative 5, plus the log of my concentration of A minus, which is here from the sodium acetate, so that's 0.040, all over my concentration of my acid, which is 0.080. Right? If I put this in my calculator, minus log of 1.8 times 10 to the negative 5 is 4.74. And then the log of 0.04 divided by 0.08 turns out to be a negative 0.30. And then that simplifies to 4.44. And so that's the pH of the buffer solution. Really not too bad. Just using the Henderson-Hasselbalch equation to solve for the pH of a buffer. So let's try a different example. So this one's slightly different, but you're kind of using the same equation. So your goal is to create a buffer of pH 4.65 using acetic acid. Here again we see it, and then potassium acetate. Given a concentration of 0.55 molar potassium acetate, determine the required concentration of acetic acid. Okay, this is a buffer problem. You should recognize that by understanding that you have an acid in the presence of a common ion. And the first thing you should write is the equation. pH equals pKa plus log of A minus. You should always be writing these equations, even if you aren't sure how to approach the problem, because you get partial credit on the exam. And so the more you write and the more you try to plug in, the more effort you give the problem, the more likely you're going to get some partial credit, even if you don't get the exact answer. So always show your work. Okay, so here I know that I'm just going to start plugging in values, okay? Because I'm looking for my concentration of HA, and now I'm given everything else, and I can do that, okay? So I know pH is 4.65. My pKa is my minus log of 1.8 times 10 to the negative 5 plus log of A minus, which is given to me as 0.55, over my concentration of HA, which is what I'm looking for. All right? Okay, so let's just start simplifying. So 4.65 is equal to, minus log of this term is going to be 4.74, as we saw in the previous problem, plus log of 0.55 over HA. And then I'm going to combine like terms. I'm going to move the 4.74 to the left, and that gets me a negative 0.09 equal to log of 0.55 over HA. And then this is where a lot of people start getting confused, because you're like, how do I get rid of this log? Okay, so the inverse of log is 10 raised to the power. So to get rid of this log, you basically take 10 raised to each side, and the 10 and the log cancel out. Right, so then let me continue my work up here. 10 raised to the minus 0.09 turns out to be very close to 0.80. And then that's going to be equal to 0.55 over HA. And then we can very easily solve now for the concentration of HA, which here is going to be 0.68 molars. So really very, very similar to the previous problem, but they're just giving you different things and asking you to solve for something else.